we don't want to lose sight of what we're doing and what our aim is. So the aim, remember, it's if you have a charge distribution, how do you get the potential? If you know the potential, how do you get the electric field? We're trying to find this new method of getting the electric field in 2 steps. We already said that this is the starting point, the definition. We define the electric field in terms of potential this way, and now we're trying to see how do we get the potential from the charge distribution. I also mentioned that we're going to do this in steps. There are several steps we're going to go through in order to get the final goal of getting the potential from a certain charge distribution. The first step was to get the difference in potential between 2 very close points. The second step, how to get the potential difference between 2 points that are very far. Now, how can we use that difference in potential between 2 points that are arbitrary 2 points, but we're going to do it for a point charge. So we're going to just put one charge in the problem and see if we can get the potential difference between 2 points due to 1 point charge. Because if we know how to do it for 1 point charge, we're going to show that we can do it for any other kind of charge distribution. Because any charge distribution in the end, it can be broken up into point charges. So this is our problem. We have 1 point charge at the origin, charge Q. And we have a point here in space with coordinates x, y, and z. The vector that points from the origin to this point x, y, and z is called r. The unit vector that points from the origin, from the charge to the point here, is called r hat. We know the electric field is kq over r squared r hat. And r hat can be written as r over r. The vector over the magnitude, this gives a unit vector, a vector with magnitude 1. So this is what we know. We've done this before in the previous chapters. We've done it in detail. We've got the electric field for different charges. Now the question is, what is the potential at point P in space due to this charge? I'm going to tell you that the potential is kq over r plus a constant, where r is the distance between the charge and the point. If I use this definition of potential as kq over r and you plug it into this equation that gives the electric field in terms of the potential, I'm telling you that you're going to get kq over r squared r hat. The proof is done in detail in the next video. If you don't want to go through the proof, you don't have to, but you can prove very rigorously that if you take the potential to be kq over r and you plug it into this equation, you will get the electric field that you know for a point charge. Of course, the proof is very interesting, so you should look at it, but in case you don't, this is how you can derive or show that the potential is given as kq over r. So we know now that the potential at a point in space that has coordinates x, y, and z is kq over r, where r is the distance between the charge and the point. So the potential is just a number. Remember, the potential is a number, it's not a vector. But if you want to get the potential difference between 2 points in space, say you have point 1 here that has r1 distance and point 2 which has r2, the difference in potential between these 2 points, remember the difference in potential is a single number. It doesn't depend on the particular path we choose to go from point 1 to point 2. And you can see that it doesn't depend on the path here, because when you take the potential at point 2 minus the potential at point 1, this constant goes away, and you're just left with kq over r2 minus kq over r1. Kq over r2 just depends on the distance between the charge and point 2. Kq over r1 just depends on the distance between the charge and point 1. So this quantity only depends on the location of the initial point and the final point. So the difference in potential doesn't depend at all on the particular kind of path you choose to go between point 1 and point 2. It just depends on the location of point 1 and the location of point 2.